So this is Xingao from the College of William Mary. Today I'm going to present our work, Reduced Cooling Redundancy, a new security vulnerability in a hot data center. So this is a collaboration work with my advisor, Dr. Haining Wang, and another professor, Dr. Xiaorui Wang. Well, as we all know, in today's data center, hundreds of thousands of servers are placed in a small room and keep running regardless of day and night. At the same time, a huge amount of heat is also generated in every second. And this heat is actually quite difficult to dissipate in today's data center environment due to the high server density. And in fact, a huge part of the budget for maintaining data center is for the cooling process. Based on a report, it said in 2014, US data center consumes 17 billion kilowatt hours of electricity in 2014, and 40% of them is consumed by cooling process. To cool down servers, today's data center are equipped with several different technologies. For example, the CRAC cooling system, the traditional computer room air conditioner system, relies on a chiller and a cooling tower to provide the coolant to absorb the heat from the air. And the liquid cooling method, you basically use some liquid-based coolant, like the water, to directly absorb the heat from the microprocessor. And also, some data centers are built in a colder environment so that they can utilize the free air to cool down servers. Well, restrained by the geographic limitation, the traditional CRAC cooling system still remains the most widely used cooling solutions. So let's take a deep look into this CRAC cooling system. So in a computer room, for high cooling efficiency, the servers are usually stacked together and divide the room into the several cold areas and hot areas. The cold air is supplied from the raised floor and flows through the backside of the server to absorb the heat. And the hot air is then returned to the CRAC system and cooled down by the chillers again. Well, in a data center, ideally, the cold air and hot air should be perfectly isolated for a high cooling efficiency. However, gaps exist between the insulation material and the server racks. As a result, the hot air generated by one server might enter into the cold areas and affect the inlet temperature of other servers, causing the air recirculation. For the CRAC cooling system, the key for the cooling cost is the supply air temperature. If we can raise the supply air temperature by 1 degree, we can save around 5% of the total budget. So, a new trend in today's data center is to raise the supply air temperature. By raising the supply air temperature, it can obviously achieve a low value of power usage effectiveness and thus save cooling costs. However, it also forces the server running in a hotter environment than before. So that's the first trend. Another trend in today's data center is the widely adoption of power over subscription. Power over subscription basically places more servers than the power capacity can support. For example, to meet the increasing demand of cloud service, the data center simply places more new and powerful servers in this data center. And on the other hand, the power capacity, power facility, and the infrastructure are difficult and expensive to upgrade. So with the adoption of power over subscription, it allows the data center to deploy more powerful servers without upgrading the old infrastructures. Well, the theory behind the power over subscription is that servers rarely meet their power peak at the same time. Well, this is true for most cases because the average utilization for a data center is around 20% and even lower. So with the adoption of power over subscription, more powerful servers also generate more heat, which further increase the temperature of the computer room. Well, with such two policies adopted into data center, it caused a new problem. which is the cooling redundancy. Well, the cooling infrastructure is also quite expensive to upgrade in today's data center. Well, such infrastructure were initially well designed to support the normal function of all servers and to handle some unexpected situation or emergency. Such cooling redundancy has been excessively consumed by such aggressive cooling saving policies. So with the reduced cooling redundancy, data centers still work well under normal cases. However, in some extreme conditions, synchronization of running intensive workload in a set of adjacent servers might cause the generation of some hotspot and even cause the overheating problems. So what's the consequence of overheating? Firstly, people have long proved that a higher temperature might increase the possibility of the hardware failure, will affect the hardware reliabilities. So it will generate, it is more possible to generate uncoverable and hardware failure. Secondly, it will negatively impact the thermal condition of other servers. This is because the existence of air recirculation, the heat generated by one server will affect the inlet temperature of its labels and causing some local hotspot. Obviously, it will raise the cooling cost because the cooling system needs more power to cool down the hotspot. What will happen if the cooling system cannot or is unable to cool down this hotspot? Then cooling failure might happen, which means the servers might need forced to reduce its operating frequency or even shut down for self-protection. And unfortunately, the service interruption due to the overheating actually did happen in the past few years. And the consequence of such service interruption is huge. So now we know the problems. The next question is that, can we intentionally, or can attacks intentionally create some hotspot and cause the overheating problems in data center? So to answer such a question, we first need to know the thermal characteristics of the servers. And also in a cloud environment, customers only hold limited computing resources. So how to maximize the heat generation with limited computing resources? Well, we conducted a testbed management study. We placed a supermicro server in a sealed environment without any window to the outside world. And the ambient temperature is around 21 degrees, cooled down by the CRAC cooling system. And we measure the inlet and outlet temperature through some temperature probes. We carefully choose some HPC benchmarks based on one previous work. It's that those benchmarks consume quite similar memory utilizations. And we run same copies of those benchmarks to ensure they consume same CPU utilization. So in this experiment setup, they consume quite similar system resources. This figure shows the outlet temperature. We can see that although they consume quite similar system resources, they actually lead to very different outlet temperature, which means the heat generation is very different. So the reason is that although the system resource consumption is similar, such as the number of CPU cycles is same, the underlying pipeline flow are different. The number of retailed instructions, the number of cache misses, the number of branch misses, and all other things are different. Those differences further cause CPU hot and leave function units idle, and result in a different amount of heat generation. So this experiment demonstrates that thermal-intensive workload can generate much more heat without consuming more system resources. And through these experiments, we can also see that the temperature increased quickly in the first several minutes. So if an attacker can run in thermal-intensive workload, he can generate a huge amount of the heat immediately. We then emulate an IaaS environment by running a couple of virtual machines on the Zen hypervisor. Each virtual machine is allocated with specific system resources. And we run all the virtual machines with 25% utilization to represent a baseline case. Then we select one or more virtual machines running thermal-intensive workloads to exhaust the host resources. So this figure shows the result. As we see, with more virtual machines under attack, it can increase the temperature to increase the server to a high temperature. So if an attacker can achieve several virtual machines co-resident on the same physical server, he can produce more heat. For the data center level, we conducted a trace-driven simulation based on CFD analysis. We basically built a 3D model of this data center in a CFD software, and we then use this software to simulate the parameters of air recirculation. So in this data center, we have 4 rows of server. Each row contains 8 racks, and each rack contains 40 servers. So totally, there are 1280 servers. And this data center is already power oversubscribed. Due to the air recirculation, the outlet temperature is affected by the outlet temperature power consumption of all servers in the room and the supply air temperature of the CRAC cooling system. The inlet temperature depends on the supply air temperature and the outlet temperature of all other servers. We use a 1-week trace from a real data center. And we start the, excuse me, the supply air temperature at 16 degrees and the red line threshold temperature at 25 degrees based on one previous work. So the red line threshold temperature means that if this temperature is reached, the server might be in danger. So it represents the occurrence of overheating. The goal of the cooling system is to keep the inlet temperature of all servers below the red line threshold. So this figure shows the inlet temperature of all servers. Each block represents the average inlet temperature of 10 servers. As we see, on the normal case, the highest temperature is around 22 degrees. Then we select some servers and switch the workload to thermal-intensive workload. And we can see that in the right corner, the servers suffer significantly a higher temperature than before. And some of them even pass the red line threshold. So note that for A and B, all the servers consumes exactly the same utilization, which means traditional utilization-based load balancing might not work well here. We further investigate the attacking efficiency for such vulnerability. So we consider 3 types of attacker. First one is random. Such attacker simply randomly choose a set of servers. The second one is rack level. Rack level attacker, we assume they can achieve rack level co-residence with some advanced networking intrusion techniques. The last type is hotspot. Such attacker can roughly infer the location of hotspot and infer the servers located in that hotspot. Such information is very difficult to obtain, however, still possible by some long-term observations. We consider 3 background workloads scenarios: high, medium, and low, and 4 different supply air temperature. So this figure shows the result. We basically have 2 major observations. First one, it would take huge efforts for random attack to cause a local hotspot of the overheating province. However, rack level co-residence can significantly reduce the attacking effort. If the attacker holds the knowledge of the hotspot, tens of servers are enough to cause a local overheating. Secondly, the attack would be more successful if it is launched when the data center is already in a hotter environment. So if the supply air temperature is raised by 1 degree, the attacking efforts are reduced to half. So which means if today's data center continues raising the supply air temperature for saving cooling costs, such vulnerability might be a real threat to those future cooling efficient data centers. For the mitigating method, we propose a dynamic thermal well load balancing with the consideration of thermal conditions and the physical locations of servers. So this figure demonstrates that it can help the data center become more resilient to such potential threat. In the future, we also plan to propose the robust anomaly detection at the chip and the server level for thermal-intensive workloads, and combine cost-effective sensing solution with proactive thermal management in the data center level. To summarize my work, we reveal new vulnerabilities of reduced cooling redundancy. The root cause is aggressive cooling saving policy and power oversubscription. And we conduct testbed experiments and data center level simulation, and we discuss mitigating method. Thank you.
So I actually have a question. In the cloud provider case, where I'm a cloud provider, do I have to a priori know what the workload looks like for all of the jobs that the clients are going to run on the system in order to do a load balancing that's thermally aware?
Well, in a cloud environment, in IaaS environment, you can basically run every workload in your virtual machine. For some other platform, for example, software as a platform, you can it basically already holds the software, but you can send a lot of requests to such software to increase the heat generation.
Any other questions? All right, let's thank the speaker one more time.
Thank you.